Hopefully it works. All right. So geometry, last time we moved on to right triangles because we can. Um, yeah, so we're about to go to right triangles. That's it. Here we are, right triangles. So the first thing we ever talk about in right triangles is basically um, Pythagorean theorem, which was discovered in Babylon, Egypt before whatever shenanigans they tell you in class. Um, okay, so the easiest way to look at it is go to length, go over here, and get this area. Basically, draw a right triangle. So cut it out. Basically, print this out and cut this portion out. I mean, I would recommend you print another piece of paper, but draw this out and then cut it out. What you'll see is that you can fit A and B into C, basically, if you do it correctly, no matter what the situation, as long as it's a right triangle, properly done. So a shorthand that geometric people do is to write it like this. I don't like it because I never use it ever again. That this format of writing it. Um, as an engineer, I never write it like that. I just see a right triangle and basically just say, yes, right triangle. So obviously you use it. That's it. That's basically how I see right triangle. You basically say, ah, that's a right triangle. Let's fix it. Yeah, that's done. That's basically what happens usually. So what I mean by that is with a unit circle, you have a SOHCAHTOA standard method. So this is a standard method of figuring out, which is SOHCAHTOA, which means the sine, opposite, hypotenuse. Oh, this is gonna be a pain in the ass. Cosine adjacent to hypotenuse. We already. Oh, right. I forgot. I changed that because I forgot to add a bunch of shit in here. The first thing I forget to add was when you come over here, I deleted the first thing in definition, which was complementary angles and whatever that was. That was like, why did I put that there? I have no idea. Instead, I put it here. First thing I write about is adjacent angles, and we have this diagram here to explain what it looks like to have an adjacent angle there. It's kind of like a obvious thing, but I forgot to add it, so we're putting an adjacent, and over here we have supplementary and complementary angles because I just forgot to add it. It might be a good idea to put a right angle there, but I didn't really want to because it's a pain to do, and still latex is a pain in the ass, so I don't want to do it. Actually, I think that was by hand, but whatever, it doesn't matter. Anyway, there's other classic definition. Oh yeah, and then I forgot to write. How could I forget this? These things. So perpendicular and parallel. I totally forgot about these. I was like, how in the world do I forget to write about that? No idea, but there you go. I did it. Yeah. Anyways, uh, okay, we're now doing right triangles. I look really different in my tablet camera than my computer camera. Just realized that. Well, it doesn't really matter. I don't really know how I look like sometimes because I look completely different for different things. Anyways, um, we're doing SOHCAHTOA next. Uh, we have right triangles here, and then the first two right triangles uh, is over here, and I realized over here I should have probably made this 0 point, 0 point, and 0 point. So these are famous right angles. I put it there because I mean honestly, there's no practical use for them in the real. I have never seen someone say, "Give me a 30, 60, 90 triangle. Give me a 45, 45." I mean, 45, 45 I actually seen in beams, but 60, nah, nah, I haven't seen that. Instead, actually, there's a reason why you would find 60. But why would you find 60 equilateral triangles? 60, and then you put an arm over here. Well, that's kind of the reason why you see 60, 30. And then 45, 45 is obvious because you see something like this. You may see something like this. You may see something like this. Um, Basically, because of that, you'll see 30, 60, 60, 30 triangle, 90 triangles. You see 45, 45, 90 triangles very often because of that thing. It's a very common engineering question. It's like the first thing I learned in statics, like the first like few things. All right, so I modified this here because I didn't like how I love the diagram that this guy made, and I'm pretty sure he made it with latex. I'm like 95% sure he used latex, and I'm not willing to spend that much time in latex to do that shit because I'm lazy and I'm not willing to draw this whole thing out in latex. Hell to the no! I am not at all. Oh, I realize right now that the because the camera's kind of I don't know. Anyway, hell to no, no. We're not writing this whole thing. I'm not writing this whole thing like this. Even though I could possibly do it with enough time. Nah, just bring this guy in. The only part I didn't like was I didn't, because of the section is a right triangle. I want there to be a right triangle there. That's the only thing I didn't like about the original image, which I fixed. But hell to no on like fixing this, doing this stuff. Like, no, I'm just gonna get it from the internet because the internet has the better version. Like, why waste more time on something that I could just get a better version? And there's an even better version in Trig. You'll see. The last right triangle. Oh, this one I definitely need to actually do it by hand because you're not gonna really make sense of it otherwise. Okay. Yeah. So CAB. As you can see, I have more energy, and that is due to not doing this at 3. Instead, doing it at almost 2 o'clock, which is probably bad. But with SOHCAHTOA, you could get these two relationships, and from this relationship, we know that this is also we know a squared plus b squared equals c squared. What does that tell you? Well, not much, but you can see that there is a division if you do a squared divided by c squared plus b squared divided by c squared. I get 1. And from that, we already know that this relationship must be true. So we plug it into here, and did I forget something? No. I don't know why it is such a confusing way, but uh, basically you find out this is a divided by c, which is over here sine theta square plus cosine theta square. And theta is just a variable, so you can change it to x if you want, which is what I think we chose sine x instead. This doesn't matter. It still gets the right answer. You get the final solution where everything is just 1, basically. And then you're done, basically. And then there's another proof over here, a basic proof. Um, what is this? Tells you you're given that these are right triangles. You're given that this is like this. In reality, if you real, I think this is right, right? I give you, no, I give you that these two are the same for some reason. Why did I do that? I don't know. I mean, technically it makes sense. A, no, I gave you this part. Okay, that makes sense. Yeah, I gave you this part basically. That's fine. That's fine. And I use reflexive about this point, I believe, saying that they have the same reflexive property. And I use similarity, AA similarity, which means angle, angle, making these similar, meaning this. Two angles are same. Yeah. Well, with that said, you can solve something like this, basically. Um, I should put more steps in there, but I'll do that later. And then we finally go to Polygon. I might add more proofs there because that sounds like boring. And obviously I have to clean these out. That's I'm not doing it right now. I'm sleepy. Another thing I fixed was finally this version. So now we're using y equal this. So at y equal 1, clearly, uh, excuse me, this equals 0, right? But because This also this 0 divided by 0 problem makes it undefined over here, so you basically have nothing over here. It was written by hand before I just changed it. Um, yeah, and this is domain, different way to write domain. And then we're done. We're done. We're done for now. I mean, there's a lot more to fix, a lot more to talk about, but at least we're closing in on 2.3, and maybe a few more questions or proofs on 2.2 is necessary. But for now, we are good. All right, I'm gonna stop my recording here and have fun with my rest of my day.